All right, let's jump right into this explainer on the monumental physical and economic hurdles of bringing high-speed internet to rural communities. Look, if you live in a big city, having gigabit internet probably just feels like a given, right? Like water or electricity. But the second you step outside those urban centers, it is a completely different reality. Today, we're unpacking the actual engineering constraints that create this digital divide, and more importantly, the really cool hybrid technologies that are finally fixing it.
I mean, that is a shocking figure, right? Up to $80,000 just to lay one single mile of fiber optic cable. But understanding exactly why trenching a cable out to a remote farm is so incredibly difficult and so wildly expensive is really the key to solving modern connectivity. It's not just a simple matter of dropping a wire in the dirt, it is a literal battle against geology, physics, and basic economics. So here is our roadmap for today. We're going to explore this step by step. We'll start with the rural digital divide, move on to the density economics problem, tackle the physics of distance, look at hybrid and space solutions, and finally talk about funding the final frontier.
Okay, starting us off with part one, the rural digital divide. You know, when most of us hear digital divide, we just think about affordability. But from an engineering standpoint, it's a profound socioeconomic chasm driven by the brutal physics of last-mile delivery and capital expenditure, or CapEx. In a densely populated area, the massive upfront cost of trenching optical networks is pretty easily absorbed. But as you move out into rural territories, the physical medium, whether that's fiber in the ground or wireless signals in the air, suffers from severe signal attenuation. Basically, the signal naturally weakens and degrades over vast distances. And when you combine that with a business model that just mathematically collapses, well, you get a divide. Which brings us right into part two, the density economics problem.
This is where population density completely breaks traditional telecom business models. Picture a city street. Laying a mile of fiber there passes hundreds, maybe even thousands of paying customers. The cost gets shared, and the return on investment is incredibly fast. Now contrast that with ultra-rural density. That exact same mile of cable might only pass one, maybe two isolated homes. You still have to pay those massive civil engineering costs to put the cable there, but you have practically no one to split the bill with.
So what does that mean in dollars and cents? It skyrockets the average cost per premise passed to somewhere between $10,000 and $30,000. Just think about that math for a second. If an internet service provider has to spend, let's say, 20 grand just to reach your house, and your monthly bill is only $80, the return on investment horizon basically stretches into infinity. Without outside help, private investment here is just mathematically impossible.
All right, part three, the physics of distance. Engineers aren't just fighting long distances, they are actively battling the Earth itself. We're talking about lithological barriers, literally solid granite and bedrock that will shatter standard trenching machines and require wildly expensive pneumatic drilling. Then you have topographical barriers like massive canyons and ridges that completely block wireless line of sight. And honestly, don't underestimate foliage. Dense tree canopies act like a giant sponge, completely absorbing radio frequency signals, especially the higher ones, which just kills wireless transmission dead in its tracks. And as you can see here, there's just no cheap cheat code through these physical barriers. If you direct bury the cable to keep it safe from the weather, you're looking at up to 80 grand a mile if you hit rock. Okay, so what if we string it up on utility poles? Well, that still costs $15,000 to $45,000 a mile in permit fees and structural engineering just to handle the extra weight. Plus, now your entire network is exposed to ice storms and falling trees.
But engineers are incredibly resourceful. Let's look at part four, hybrid and space solutions.
Since running fiber the entire way is usually a non-starter, operators use a hybrid toolkit. Step one, you run a high-capacity fiber line to a central high-elevation point in a community. Think like a water tower or even a grain silo. Step two, you mount high-powered fixed wireless access antennas to that silo, and you beam the high-speed signal over a 5 to 15-mile radius out to the surrounding farms. By doing this, you're bypassing the insane cost of trenching that final mile to every single house, which can slash last-mile costs by up to 80%. It's brilliant.
But what happens when a homestead is so isolated that even a fixed wireless tower on a silo can't reach it? I mean, what if the population is less than one household per 10 square miles and you're surrounded by mountains?
Well, you luck up. The answer lies in the vacuum of space with low Earth orbit, or LEO, megaconstellations. We're talking about networks of thousands of interconnected satellites orbiting the Earth. And the coolest part? They use optical space lasers to route data from satellite to satellite. because light actually travels almost 50% faster through the vacuum of space than it does through glass fiber in the ground. These lasers completely bypass terrestrial geography and route data incredibly fast. Now, I know what you're thinking. Satellite internet isn't exactly new, but actually, scratch that. This architecture is new. Legacy satellites were parked way out at nearly 36,000 kilometers away. That distance meant your data had a massive commute, giving you a crippling 600 millisecond lag. But these modern LEO satellites, they orbit between just 500 and 1,200 kilometers above us. That proximity drops the latency down to a snappy 25 to 45 milliseconds. That is fiber-like performance that finally allows for real-time video calls and cloud computing for literally the most isolated people on the planet.
Finally, let's wrap up with part 5, funding the final frontier.
Even with space lasers and hybrid networks, the math still needs a push. Recognizing that the free market alone can't fix this, remember that infinite ROI horizon we talked about? Governments are stepping in. Massive subsidy frameworks like the BEAD program in the US and universal service funds globally are injecting billions of dollars. This public capital is expressly designed to offset those astronomical upfront construction costs so network operators can actually make the math work. And they aren't just throwing money around blindly. These funds meticulously target very specific areas. They look for unserved locations, which means places lacking even 25 megabits per second, and underserved locations, which lack 100 megabits. The goal here is to ensure that only reliable, long-term infrastructure gets funded. We're talking fiber and licensed wireless, making sure we actually bridge this gap for decades to come, rather than just putting a temporary Band-Aid on it. So, as hybrid networks and space-based lasers finally connect the most remote corners of our planet, it leaves us with a pretty massive question. What incredible human potential is going to be unlocked when this digital divide is gone for good? Imagine a student on an isolated farm taking global university courses in real time, or the boom in rural economies and remote telehealth. We are literally watching the spatial economic chasm close before our eyes. Thanks so much for joining me on this explainer today. Keep looking up, and I'll catch you on the next one.